Howdy, we are the UAS Cone team. My name is Faheem Noorani, and our team consists of Shreyas Choudhary, Alex Ramponi, Braedon Perini, and Jesus Ramos. Our problem statement. Currently, it is tough to accurately distinguish if a drone flies over a cone in a course by the drone flight instructor even with current camera technology. The problem with clearing drone courses that are small, large, difficult, or easy is that there is no signal or sign letting the instructor know that the drone pilot is clearing the cones in the course accurately. To solve the problem, we created a cone that uses two microwave sensors and a Raspberry Pi that detects if a drone passes over the top of it in a range of 4 to 7 meters. If the drone passes over the cone in the range, the beacon light will illuminate to signify a flyover. Here's a demo. The distance of the drop from the cone is 5 meters. As you can see, we are standing 5 meters away from the cone. The height of the drop is 2.67 meters, as you can also see from our measure. Once the beacon light is off, the system is ready to detect. The object is dropped from 2.7 meters high in front of the cone. As you can see, when the cone detects the object, the beacon light will illuminate and stay in the position until the instructor pushes the reset button in the application. Just like before, when the light is off, the system is looking for the object, and once it is detected, the light will stay on until it's reset. Here it is one more time. Thanks.
Hi guys, my name is Jesus Ramos and I'm a part of the UAS Training Cones team. My team members are Alex, Shreyas, Faheem, and Braedon. Okay, so our project is a motion-controlled lighting system that activates a beacon light once a drone has cleared an airspace over one of our designated cones. This essentially provides accuracy for drone instructors while observing drone pilots and students clear drone training courses. The system is powered by a few wall adapters and monitors motion with two microwave sensors. The logic is condition based and sends a signal to the relay, which then activates the beacon light, and the Bluetooth is controlled here by the Pi as well. Finally, the Bluetooth application serves to display the cone status and reset the lights.
And now I will talk about technical design. The overall cone design, we have a microwave sensor to detect if there is an object up to 6 meters away. We will call this the far sensor. We will then have a second microwave sensor detect if there is an object in the dead zone, which is up to 4 meters away, and we call this the dead zone sensor. If the far sensor triggers while the dead zone sensor does not, then we know there is an object in our desired range of 4 to 6 meters, so we turn on the light. The light is turned on through a BJT and a relay hooked up in series, which gets the power output to the light. The app can then be used to look at the state of the cone, as well as send a reset signal to turn off the light and start the process over again. For the Raspberry Pi code, we have a bash script that automatically starts our Python program when the Pi boots up. In this Python program, we keep ourselves in a main loop where we constantly check if the long sensor has triggered recently and the dead zone has not, and if these conditions are met, the code will then turn on the light. These sensors are updated through interrupts from their two GPIO pins, where the time of the interrupt is recorded so that the main loop can check whether the time of detection between the two sensors is great enough. The light is then turned on by simply turning on one of the GPIO pins, which connects to the BJT, which connects to the relay, which turns on the light. For the app, there's two main screens. The app will start off in a connection screen where the user must press connect, which attempts to establish the Bluetooth connection to the cone. It is also required that the Bluetooth setting on the phone is on already and it has been paired up with the device. After this connection is made, the app will then transition to another screen where you can see the display of all the cones that the app is connected to. Each one will have a status which is indicated by a light color, and there will also be a reset button and disconnect button on the screen. The reset button will be sending a Bluetooth signal to the cone and will await a response from the cone to make sure that the updated state is processed. If there is ever a time where the app is unable to communicate with the Raspberry Pi, the app will then know there's an error and check whether or not the error exists in the phone itself or from the connection to the Pi, and will then output the corresponding error message to the screen. The only library we used was the Blue.Dot API, which we used on both the Raspberry Pi and the app to send and receive Bluetooth messages. Here's our main CDR document. So we start off with power going into our first block initialization, which will utilize the Pi and start sending signals to the other systems. It is constantly sending out an initialization signal to the signal processing block 4. This is to show that the initialization process is still going on. After the initialization, it will hopefully create the Bluetooth connection to the application. It will also be sending an initialization complete signal to block 2 of the detection system. The next step is for the detection system to start looking for whether there's a detection or not. It will utilize both of the microwave sensors and look at the object, and then will output a detection signal, which will be 1 if there's a detection and 0 if there's not a valid detection. The next block is the application, which is block 3. This utilizes the Bluetooth connection established, the app itself, a connect button on the app, and a reset button on the app. And with all of these, it will create a display as well as send a reset signal to signal processing if there is a reset command pressed. For the fourth block, signal processing, it will utilize the initialization signal, which starts it as well, the reset signal and a detection signal, and will then output a state which goes into the application and the light system in order to show what state the cone is currently in. The fifth block is the signal to light system, which looks at the current state of the cone as well as requiring power and will then turn on or off the light. This is utilizing a relay and beacon light to create such light. This is our block 2, which is the detection system. It utilizes 2 microwave sensors for the far range and the dead zone, and in 2.1 it'll send these times into our next block, and after one of these times is processed, it'll instantly go into block 2.2. Block 2.2 will then look and see whether or not there has been sufficient time passed from the far sensor and the dead zone sensor, and if there has been, and the far sensor time is recent, it will then output the detection signal to 1, otherwise it will keep it at 0. After this process, it will then loop back into 2.1 and continue this loop for the remaining duration of the procedure. This is our application block. This part in 3.1, the block is to set up the Bluetooth connection. It first looks into the Bluetooth connection that is being output from the Pi from the initialization, and then we'll wait for the connect button to start the connection process. After this, it creates an established connection which is used for block 3.3. Block 3.2 utilizes the input from the state and the app itself to start displaying what the app should show. Block 3.3 utilizes a reset button, and the established connection will quickly send out the reset signal as soon as the reset button is pressed. This is inside block 3.2. As you can tell, it looks at the state for 3.2.1 and then will output the corresponding state for the display so that the display can be created based on the state. This is our block 4, which is essentially the state machine of our cone. It starts with initialization, which is block 4.1. It will then, after successfully completing initialization, it will go to 4.2, which will wait for a detection signal. Once the detection signal is read, it will then go into 4.3, which will then wait for a reset signal. After this, after hitting a reset signal, it will go back into 4.2 and wait for the next detection. If at any point there's an error, all 3 of these blocks will go over to 4.4, which sends in error handling and will then move the state to a different state. This is our block 5. So after seeing the state, we will then change it into a light output. If there's an error state, however, it goes into the error state and might have an issue, but we'll try to send an error signal to the light. If the state is 0, which is initialization, or 2, which is the triggered state, it will send that the light should be on. If the state is 1, which means it's on standby, then it will send for the light to be off. And that is our entire technical design.
I'll be talking about our internal and acceptance testing for the cones. So the very first test we had was the initialization test, and this test was to basically let the user know that the cone is ready to use when it's plugged into the power. So basically what will happen is the light will come on, and then the light will stay on for usually about 30 to 40 seconds depending on the Raspberry Pi's boot up speed, and then the light will turn off. When the light turns off, this signals to the user that the cone is ready and you can connect the phone and use the app as intended. And then so for the basic drone detection test, this is to check if the cone can read an incoming object consistently. So we were going to test this using a drone flying at certain ranges above the cone at an average speed, but due to the coronavirus, we can't do that anymore. So what we did is we measured out 4 meters from the cone, and we walked in from far out and stopped when the light was detected. So the goal was for this to be 4 meters out in a 5-minute radius, which was achievable. And then so our next test was the max speed drone detection test. So once again, just like the basic detection test, this was very hard to test without a drone. So what we did is we had to improvise. So the original plan was to test out between different heights between 4 and 10 meters while flying the drone at 22 miles an hour. So in order to achieve this in the most repeatable way possible, we improvised by standing the maximum distance we could get of 5 meters away inside my living room, and we dropped a pillow from 2.67 meters from the ceiling. So we did this consistently each time to allow it to pick up speed, and then the cone would trigger when the pillow would drop. Another thing we ended up doing is we would have to make sure we stood still before dropping the pillow, just to prove that since we were basically in the detection range, that it wasn't us the cone was detecting. The next test we had was the dead zone non-detection test. So this was to see if the cone will detect anything between 0 and 4 meters. And so once again, we had to improvise on this test as well. So the initial plan was to just fly the drone at different ranges between the 0 and 4 meters. But what we did instead is we took a pillow and we started in front of the sensor, and we just kept waving the pillow in front of the cone to signify motion. And then so once the cone light would go off, we would record the distance I was at, and it was usually right around the 4 meters. And then for the mobile application test, basically this was allow us to test the functionality and ease of use of our Android app. So what we would do is we would start up the cone and connect to the device, and then we would check to see if the cone was in standby mode from the app. And then from there we would activate the cone and make sure that the UI updated to say active. And then on top of that, the Android app is nice because you can turn off the cone's light from there. You don't have to reboot the system each time. Lastly, we have the mobile application error test, and this was to allow the user to troubleshoot the cone. So it's hard to tell what could be going wrong, so we tried to handle as much as possible on the mobile phone. So the two things we were able to catch was when the phone's Bluetooth was disabled. The app would notify the user and put an error message on the screen saying, hey, this needs to be enabled in order to use the cone app. And the other part we were able to fix was when the Pi is disconnected from the phone due to either lost connection or power outage, the app will display an error message to basically get in range, and if you're in range, you should restart the cone since something may have crashed.
Let's take a look at our CPM before Corona. Coming into spring break, we were actually in a fairly good position, other than the fact that we had to finalize on one of our sensors. Our plan A was to use the ultrasonic sensor, and our plan B was to use the microwave sensor. As we dug into spring break, we realized we should probably test both of them together so that if plan A fails, we have plan B ready to go and there's no delay. In addition to that change, we actually gave ourselves 7 extra days to wire up the cone and 7 extra days to integrate all the parts and make sure they all work together, so that includes testing. So our overall critical path went from 42 days to 59 days. So let's take a look at our Gantt chart here, and if you can see, we were behind on finalizing a sensor before spring break, but since we made that decision to split that task up and do it at the same time, we went ahead and finalized the sensor before physical implementation of the project, so there was no delay on that part. A major change that we had on the Gantt chart was one of our group members always had to be there to physically test it, and so we gave ourselves more time to complete that part. So as far as how Corona affected this whole project's course of action, we got $50 extra thanks to Dr. Murphy and the department. This way we could order new tools that we needed to finish the project. We also coped with Corona by being really responsive on GroupMe and downloading TeamViewer so we can actually make changes and see what's going on in the Pi, and just joining these Zoom meetings so we can provide intel and what we have to offer.
Future work. In the future, we would improve the sensor accuracy so it can detect faster moving objects and implement methods to catch false positives. Also, we want to build a proper stand that is attached to the cone for the beacon light. This would facilitate transporting the cones to a new location as well as have the light at a higher position for more visibility. Lastly, when the phone application launches, we would want the application to automatically connect to the cones that are in range. Thanks. I'll pass it off to Jesus for any questions.